In this chapter on basic probability, we're going to be looking at quite a few different features about probability. We're not going to get too in-depth into probability, but what we're going to do is we're going to kind of pick out the information that we need in order to use a normal distribution and a t-distribution eventually. So to start off with, we'll talk about randomness and probability. We'll talk about different types of probability models. And really importantly, we'll be talking about the differences between a discrete distribution and a continuous distribution. There's three basic rules of probabilities that we'll cover. We'll also talk about continuous random variables that will be directly related up here to our continuous sample spaces. And then we'll end with talking about risks and odds of particular events. So to get started, let's go ahead and define a random event. So when we define a random event, basically we're saying, you know what, there's outcomes that we don't know about. We don't know what there's going to be happening, let's say, next time you flip a coin. So an example of a random event would be flipping a coin. And of course, rolling a die. Driving your car to work. Will you be in an accident or not? Okay, taking an airplane flight, will it be on time or will it be delayed? Those are all random events. But even though they're random and we don't know about the particular outcome, there's some sort of a pattern or a distribution that I can do some prediction on based on a large number of repetitions. So for instance, we know a particular airline has more delayed flights than others. Over long term, we start to see that pattern. So these are all examples of random events. Of course, we can add airplane flight, whether it's delayed or not. Okay, and it also could be if you're taking a particular medical test, whether you have a positive or negative result. Now that one's not as random because there's some underlying effect, but still, when we talk about whether you have a particular disease or not, it seems to be random. Unless, of course, it's based on something like if you're a smoker, it's not random whether you get cancer. The odds seem a lot higher for that. Now, once we start talking about probability, we have a particular definition that we can look at here. Probability of a particular outcome of a random phenomenon, so like flipping a coin, rolling a die, etc. It's the proportion of times that the outcome would occur in a very long series of repetitions. So this very long series of repetitions is a very important idea. This is kind of the same as the idea of a long-term relative frequency. So when we talk about probability, we're talking about the outcomes that we're interested in, and it could be one or more outcomes, over the total possible outcomes. And we'll look at a really easy example here. For instance, if I wanted to talk about the probability of getting ahead when I flipped a coin has two sides, so that's the total number of possible outcomes. And out of those two possible outcomes, one of them is ahead, so 1/2 or 50% or 0.5. Same thing when we roll a die. So when we roll a die, I could look at what's the probability of getting an even number when I roll a die. Well, the total number of outcomes when I roll a die is 6. So again, the total number of possible outcomes. And then even numbers are 2, 4, and 6, so I get 3 out of 6. Now again, because I have 2, 4, and 6 in something called the sample space that we'll talk about here shortly, so I get 3, 6, 1/2, 50%. We can think about that quite a few different ways. Next thing we want to look at is births. So if we talk about when a child is born, there's two different possible outcomes. There's male or female, and then we can talk about the probability of each. Now, we're kind of in our mind, we're always trained to think that the odds of a girl or a boy are equal, but that's actually not quite the case. Let's look at some data. So here's some data that's been collected. It was collected over the years 1990, 2000, 2002, and 2006. Now what this table is saying, we're keeping track of male and female births. In this particular case, there was 2,129 males born, and in females, there was 2,029 males born. Of course, this is clearly not world population. It's probably in a particular city or a hospital. And what we can do then is we can look at 2,129 divided by the total. Now, the table doesn't give the total, but the total for this particular year would be 4,158. So right here, the total is 4,158. Now, if I talked about the proportion of males then is 21, 29, divided by 4,158. And if I divide that out, I get 0.512, or about 51.2%. Now, if we were to talk about, let's say, 10 births in a hospital, we could get all 10 to be males. But what we would expect in the long run is the number of males and females to about even out to 50% each. But as we can see here, as the same process has gone through, the percentage of males, or the proportion of males, seems to always be consistently slightly over 50%. So exactly the probability of a male isn't 50% like we would expect. It's about slightly over 50%. This particular data set indicates that it's about 51%. So again, this is based on long-term relative frequency. This is not just out of 2 births. This is out of many births. So if we could total these up, we could look at the total that we're talking about. But we can see the proportion of males born is actually a little bit higher. Now, if we were to check the proportion of males 20 years from these births, we'd actually find that it's less than 50%, because males have a little bit higher death rate. Children, teenagers, etc. have a little bit higher death rate, and so the proportion of females is actually a little bit higher once you move on in time. The next thing we're going to do is we're going to talk about probability models. Now, basically, a probability model is a mathematical description of a random process, and it consists of 2 parts. The first part is the sample space, and we'll talk about the sample space in a little bit. And then the second part is a probability assigned to each of the values in the sample space. So for instance, if we were talking about rolling a die, our sample space would be 1, 2, 3, 4, 5, and 6. So let's go ahead and look at that example. So if we roll a die, so our sample space S would be the outcomes. It would be 1, 2, 3, 4, 5, 6. Now, if this is a fair die, then what would happen is with each one of these values that I have in the sample space, I'd have a probability assigned to each one of those. Now, there's a lot of different ways to represent this probability that's assigned, but you could do something like the probability of rolling a 1 is 1/6. The probability of rolling a 2 is 1/6. Now, these are equally likely, mean all possible outcomes have the same probability, but that's not always going to be the case. So another way we could represent it is by a probability mass function, where we could actually look at the outcomes, and we'll call the outcome some possible value of x, and then look at the corresponding probability. So I could get a 1, 2, 3, 4, 5, or 6, and then I could list their corresponding probabilities. So this is kind of an easier way to keep track of things in a table. And again, it's called a probability mass function or a probability distribution function. But this is actually the probability model. And again, it has 2 parts. It has the sample space, the total number of outcomes, and the corresponding probabilities. Let's go ahead and look at a probability model or a probability mass function for the data that we just looked at previously. So these were births. And when we had a birth, we kept track of gender. So when we had a birth, we recorded male or female, and then we had the corresponding probability. And this value of x I keep using. It could be y, it could be g for gender, it doesn't matter, but typically we just use a generic x. And we found that for males, the proportion was 0.512, and of course for females then would have to be 0.488. Now, how did we intuitively know it would have to be 0.488? Well, if I only have 2 possible outcomes and the probability of a male is 0.512, that means the other outcome has to have the sum to 1 of 100% probability. So this is actually called the complement of an event that we'll talk about eventually. But this is, again, is the probability model for the example that we just looked at with births and gender. Now, with each of the models that we just looked at, there's something kind of interesting here. First of all, the outcomes here are numbers, 1, 2, 3, 4, 5, and 6 when we roll a die. So this is a quantitative or numerical random variable. Down here, for births and gender, our outcomes were male or female. So this is an example of qualitative or categorical random variables. So even for categorical or qualitative data, I can still produce this probability distribution or this probability mass function. Now what I want to do is I want to kind of skip around a little bit and only talk about quantitative data. So for quantitative data, I have 2 subsets that I want to look at. And again, another name for quantitative data is numerical. So for quantitative or numerical data, I have two outcomes that I can look at. I could look at outcomes that are discrete, which is what we were just looking at when we rolled the die, and I could look at something called a continuous sample space. So our first one we want to look at is a discrete sample space. Now for a discrete sample space, I look at discrete variables, and discrete variables can only take on certain values. Usually they're like an integer value, like 1, 2, 3, 4. They're not a continuous value. For instance, if I talked about the temperature of a patient coming into the emergency room, their temperature could be anything. Let's say between 95 and 105, and it could be any value. Now a thermometer might give it to the nearest tenth, but it's actually a continuous value, meaning it actually could be anything depending on the preciseness of the instrument that we use to measure the temperature. So let's go ahead and write that description out for a discrete sample space. So again, we have discrete values that can take on only certain values in a sample space. And usually they're a whole number, an integer value, but not necessarily. Now as a quick caveat, we are talking about quantitative or numerical variables, but under the discrete case, I can also talk about categorical here a little bit as well. Again, another name for categorical is qualitative. So we're going to look at an example where we talk about blood type. Well, blood type is certainly not a numerical value. It's O positive, O negative, B positive, B negative, etc. Definitely categorical, but they can only take on particular values. So again, even though we're talking about quantitative and numerical, one subdivision of quantitative and numerical is discrete sample space. Well, discrete also goes with categorical as well. There's another spot that we can talk about here about continuous sample spaces. Now, a continuous sample space, we are specifically talking about numerical values. We talked about temperature. You could also talk about time. How long do you have to wait before you have your spot in the checkout lane? Typically we'd say, 1 minute or 2 minutes, but actually that time is continuous over any value from 0 to infinity, and hopefully you're not in line that long. So continuous variables can take on one of an infinite number of possible values over an entire interval. Let's go ahead and write that definition out. So some examples here for a continuous sample space would be something like wait time. So some examples here would be wait time, temperature, speed of your car. Now if you have a digital readout on your dash, it probably is only to the nearest mile per hour, but really it's a continuous random variable. It could be anywhere between, let's say, 0 and 100 miles per hour. It just depends on the accuracy of your measurement device. So these are all different examples. What I would like to look at next are two specific examples. The first one we're going to look at is blood type, and the second one we're going to look at is cholesterol level. So let's start with blood type. Well, first of all, when we talk about blood type, we can kind of look back up here. It's discrete. It can only take on a certain value. And is it categorical or is it numerical? Well, blood type is definitely categorical. So this is an example of discrete and categorical probability mass function. Now here my sample space are the total listing of all the possible outcomes for blood type. So I could be O positive, O negative, A positive, A negative, etc. So there's 2, 4, 6, 8 different possible outcomes here. Now this picture is a representation of our probability distribution because it has each blood type and its corresponding probability. Now if you had people come into a blood bank to donate blood, you wouldn't expect, if I had 100 people come in, that exactly 38% would be O positive. What would end up happening here is we would see over the long term, I see the trend that about 38% are O positive. So again, this is based on long-term relative frequency. So here's my sample space S, and here's the listing of the corresponding probabilities. So this is kind of a pictorial view of a probability distribution. Next we want to look at a continuous random variable, and this would definitely be from the numerical spot. So again, continuous and numerical. Now if you talk about cholesterol level, we'll call our sample space S. Well, I guess you could have 0 cholesterol, and it could go clear up to, I guess, infinity. At some point, though, you'd probably think death would occur before you got to an infinite amount of cholesterol. So this would be representing cholesterol level. Now, interestingly enough, infinity probably isn't reasonable, and 0 probably isn't reasonable either because there's naturally occurring cholesterol, but this would definitely cover the span. We could probably tighten it up a little bit as well, but this definitely covers the span of cholesterol levels. Now, when you report your cholesterol, it's usually to the nearest integer, but really our measurement device could give us very precise numbers anywhere between 0 and infinity for this example. The next thing we want to look at after we've talked about these discrete distributions is talking about how we find sample spaces, how we come up with these. And one way is with a tree diagram. So let's go ahead and look at sample spaces. So for our first example under sample spaces, let's suppose, this is an S with a P, means suppose, a couple wants 3 children. The question is, what are the possible sequences of boys and girls? Now, you might say, oh, you could have 0 girls, you could have 1 girl, you could have 2 girls or 3 girls. And of course, if I have 3 girls, that means I have 0 boys, 2 girls means I have 1 boy, etc. But this talks about the possible sequence. So one thing that you could do is you could have 3 boys, boy, boy, boy. Well, one way we can kind of keep track of this is with a tree diagram. And it's not necessary. This example that we're looking at isn't all that complicated. But one thing that we could do is talk about a tree diagram. So I could have a boy or a girl with the first child. Then with the second child, I could have a boy or a girl as well. And you can see that these get out of hand pretty fast. Only with 2 options here. They're already getting large. So again, and then the third child could be a boy or a girl. Now the reason these are branched off is because I'm taking into account all the cases that have already occurred. So for instance, this branch of this diagram would be boy, boy, boy. This branch would be boy, boy, girl. And then we would go through the same process. This would be boy, girl, boy. This would be boy, girl, girl. And this is just a way to kind of organize things. Now notice I have 4 cases where the first child is a boy. That kind of indicates to me that I should see some patterns here. I should have 4 cases where the first child is a girl. And that's this branch. So this branch goes girl, boy, boy. Girl, boy, girl. This is girl, girl, boy. And girl, girl, girl. So this is my sample space. So my sample space basically consists of these outcomes. So there's a listing of my sample space. Now, what if I had 20 children? Well, if you had 20 children, this tree diagram would get out of hand pretty fast, and I definitely don't want to write them all out. I'd have a lot of different values here. So how could I have figured out in advance that I would have had 8 outcomes? Well, it's a basic counting principle. So if you want to think about this, you could say this is your first child, second child, and third child. Well, for your first child, there's 2 possible outcomes, male, female, or boy, girl. For your second child, there's still 2 possible outcomes, male, female, or boy, girl. And for my third child, I have 2 possible outcomes, male, female, or boy, girl. And then I multiply these together. 2 times 2 times 2, or 2 cubed, which is 8. And 8 directly relates to the 8 outcomes that I have right here. So suppose you have 20 children. We don't want to know what the possible sequences are. We don't want to write them out. I want to know how many possible sequences. without having to write about. Well, this is a huge number. Following our same pattern that we just looked at, this would be 2 to the 20th. Now 2 to the 20th, if you grab your calculators, you can tell is a very large number. There'd be 1,048,576 of these listings. You definitely don't want to write those out. But it would still tell me what the denominator is. It would still say this is the total number of outcomes, and then the numerator could talk about what's the probability of having all girls then. That would be 1 out of 1,048,576. So for this example, we talked about ordering or finding the number of sequences we have for 3 children if they were boys or girls that we were counting. Usually then you define a random variable. So next thing we usually define a random variable. So let's say I'm going to look at the random variable x. X equal the number of boys in a family of 3 children. So this is referring directly to our example here. Well, the sample space here then are the values that x could take on. So my sample space for this event would be I could have 0 boys, I could have 1 boy, 2 boy, or 3 boys. I can't have 4 boys if you only have 3 children. So if I want to talk about the probability that's associated with these, the probability of 0 boys looks like, in this particular case, that it would be girl-girl-girl combination would be 1 out of 8. So my probability I could talk about in terms of a probability table. Now again, x is the number of boys. I can have the corresponding probability of x. Now this is assuming equally likely outcomes. And so we've already talked about how the probability of a boy is actually a little over 50%, but I'm going to look at this in terms of equally likely outcomes to kind of simplify the probability distribution. So x is the number of boys, and to make it even easier so I can remember what I'm keeping track of, maybe I'll put b here for boys. Well, the probability of 0 boys is 1 out of 8. The probability of 1 boy, let's kind of pop up here. Here's 1 boy, here's 1 boy, would be 2 out of those 8 outcomes. The probability of 2 boys would be boy, boy here, 2 boys, boy, boy here, and boy, boy here. So I had 1, 2, 3 of those. Now let's look here. I have 1/8 plus 2/8 is 3/8. 3/8 plus 3/8 is 6/8. So let's see if we have any mistakes here. Because we would have expected to see a 3/8 here. Oh, here it is. Here's my single boy here. So that would make this a 3/8. And then the probability of all 3 boys we can see is this one case left up here, and that would be 1/8. Now, a couple quick things. 1/8 plus 3/8 plus 3/8 plus 1/8 sums to 8 over 8, which is 1, and that's a characteristic that I always have to have in a probability distribution. The sum of the probabilities always must be 1. And this is important. Put a big star by it. So another way we'll see this is the sum, Greek letter sigma. The sum of the probabilities of the boys has to equal 1, and we can see that that's true in this case. Now another thing we could do is look at, let's say, the amount of time that it takes to go to school or to commute to school. And again, our time would be anywhere between 0 and hopefully not infinity, but 0 and let's say 2 hours. So any possible value could be recorded there. Now the problem is I can't make a table of all those possible values, and so usually you have to use a function to describe that. And that's really what we're working toward here for a continuous random variable, is to use some sort of a function to describe the probability and then use this function to determine probabilities. So for a discrete random variable we can make a table. For a continuous random variable I need some sort of a function to work with. Now whether it's discrete or continuous, there's 3 basic rules of probability that have to be followed. So next let's go ahead and look at some probability rules. The first probability rule is all the probabilities that we see have to range between 0 and 1 and can be equal to 0 and equal to 1. So our first probability rule is for any event A, the probability of event A has to range between 0 and 1. Now notice I have an equal sign here. It can equal 0 or it can equal 1. So this particular event, 0, has no chance of occurring. And up here, the probability of 1, this means an event has to occur. Now, when we talk about probability, we talk about things like 50%. Now, 50% is a decimal of 0.5, which ranges between 0 and 1. So, percentage-wise, they fall in here as well. Now, sometimes you'll see somebody say, what's the chance of rain tomorrow? And they'll say 120%. That has no mathematical meaning. It just is kind of hyperbole talking about extreme events. So, our second rule of probability is the sum of the sample space must equal 1. And we just talked about that and showed that how that worked with our example of 3 children in a family. So the sample space, the sum of the probabilities in a sample space must equal 1. The third probability rule has to do with complements. So the probability of A not occurring, and we use A prime to mean A not, is 1 minus the probability that A occurs. So this is called the complement of an event. This means A complement. Now, A prime could represent A complement. Sometimes you'll see an A with a little c to represent complement, but any of those ways to represent a complement works. So if we knew the probability of a girl was 50%, the probability of a boy would be 1 minus 50. Probability of not girl would be another way to say that, would be 1 minus 50% or 50%. So these are our 3 rules of probabilities, and you'll definitely want to know these. Good fill in the blank or something on a test or a quiz. So know these. They're very important. Now, also going along with the probability rules, we have to talk about some different types of events. So we've talked about how events can occur, you know, when we roll a die, 1, 2, 3, 4, 5, 6, etc. But we also need to talk about how we combine events. And so now we're talking about multiple events. The first thing I want to talk about are disjoint events. Another name for disjoint events are events that are mutually exclusive. Now, the best way to represent disjoint events, or to show you what disjoint events mean, are to draw a Venn diagram. So I'm sure you've seen some sort of a Venn diagram before. And we're going to just talk about the 2 event case. So in this case we have event A and event B. In this case we have the same events, we'll call them C and D, but there's overlap now. In this particular case, A and B are disjoint. Event A and event B are disjoint. They have nothing in common. They have no overlap. They have no outcomes in common. So event C and D, they have this outcome in common. They have overlap here. So in this case, A and B are not disjoint. They have outcomes in common. So first of all, when we talk about disjoint events, basically disjoint events can never happen together. They can have no outcomes in common. So let's go ahead and look at some examples. And Venn diagrams really help show disjoint events. So now we need some events. And we'll come up with some that are disjoint and some that are not disjoint. So let's say I roll a die. And when I roll a die, I keep track of whether my outcome is even or odd. So you roll a die, and you know whether the outcome is even or odd. So the even values would be something like 2, 4, 6. Odd values would be 1, 3, 5. There's no outcomes in common here, so therefore the outcomes, whether they're even or odd, are disjoint events. Let's go ahead and look over here. Roll a die, and I record whether it's even or a multiple of 3. So I'm going to call it E for even, M for multiple of 3. Well, the even numbers are 2, 4, and 6. 6 is both a multiple of 3 and it's even. Now over here, the other multiples of 3 that could occur are 3 and 6. So this outcome that's in common is in the intersection of the events. So again, this is called the intersection. Now you might say, well, what about 9? Well, we can't get a 9 if we roll a die, so I can't list that as a multiple of 3. So important thing, this is the intersection of those events. Now that we've described disjoint events, we can talk about the addition rule for using disjoint events, how we find probabilities. So let's go ahead and look at the addition rules. Now usually we'll only look at 2 cases, but in class we might do a 3 case, working together to kind of see what the effect is if we have 3 different outcomes. So let's go ahead and look at the addition rule. This is just one rule, so I better change that to just one rule. We have 2 rules. We have one if we have disjoint events, and we have another for non-disjoint events. So let's go ahead and look at the one for disjoint events. When 2 events are disjoint, the probability of A or B is just adding the individual probabilities together. The probability of A plus the probability of B. And again, this is for disjoint events. So I'll just draw a quick little picture here of disjoint events. They have no outcomes in common. Now the second case here is for any 2 events, disjoint or not. So for any 2 events, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Now why do we have that subtraction there? So let's have a look. Well, this is an interesting look at this. So let's make this a nice big Venn diagram because we're going to have to talk about this intersection. So we have 2 events, A and B. These could be any events, disjoint or not. I'm going to give an example of events that are not disjoint. So it says to find the probability of A or B. Well, first of all, if we looked at a Venn diagram here, the probability of A or B would be this shaded area, everything shaded. Well, to find this probability, it says, you know what, let's take the probability of A occurring, and then let's add that to the probability of B occurring. That makes sense because we want this shaded. But notice in the middle here, how many times did we count this intersection? We counted it once with A and once with B, so it's been double counted. So that's why we have to subtract out the probability of A and B. So this spot right here is called the probability of A and B. So we double counted it. We counted it once when we talked about the probability of A. We counted it again twice when we talked about the probability of B. So I have to make sure that I subtract it to represent this. So, a couple quick notes about shading Venn diagrams. If we have 2 events, this shading, just like we showed up above, is A or B. This shading in the middle that we have here is the probability of A and B. Now let's go ahead, now that we know the difference between or and, let's talk about this one. If I have disjoint events, what is this intersection? Well, it doesn't exist. So up here when I have disjoint events, the probability of A and B is 0. So if I have disjoint events, this piece falls out, and I'm just back with this formula. So again, for 2 events that are disjoint, the probability that they intersect is 0. They have no intersection like my other picture does. So it's important to know whether your rules are supportive of a disjoint type of events or a non-disjoint. But actually, you know, if you understand here in this particular case that their intersection is 0, this formula works for both cases. But you will definitely want to know this as well. Very important. Now let's go ahead and look at an example where we were talking about our blood types. So as before with our blood type example, I have each of the possible outcomes with their corresponding probability. 38%, 7, 9, 2%, 34, 6, 3, and 1%. AB negative is 1%. So what I'm looking at here then is I'd like to find some probabilities that correspond with this. So I want to answer some questions based on this information. So let's go ahead and look at our first example. What's the probability that a randomly selected person is O positive? Well, that looks like it's 38% or 0.38. We usually write things in terms of a decimal. I could also look at another one. What's the probability that a randomly selected person has any blood type? Well, we can see here, throwing logic out the window, they have to be one of these. But any blood type, I would take and add up each of these blood types. 0.38, 0.7, 0.9, 0.2, 0.34, 0.06, 0.03, 0.01. And they better sum to 1. If I find a person that doesn't have one of these blood types, then clearly we've missed out on some information here. So this is our sum of our probabilities, has to be 1 information. Another question. What's the probability that a randomly selected person is not A positive? So not A positive. Now you might see this written a lot of different ways. You might see A positive prime, which would be kind of weird because you have 2 superscripts there, or A positive complement. Well, the easy way to calculate this is to not come over here and say, okay, here's A positive. I want to add up everything but this. The easier way is to talk about the complement and say, well, the total probability is 1, so I could just take 1 minus the probability that a person is A positive, which was 0.34, and I would get 0.66 here. Now, if I had gone through and added up all of these probabilities except for A positive, I would have gotten 0.66 as well. But you can see that the complement makes this a lot easier. Let's look at another one. Let's look at the probability that a person is from blood group O. Now notice I did not say O positive or O negative, I just said from blood group O. Well, there's 2 possible outcomes here. It could be O positive or O negative. Now remember, can a person be both O positive and O negative? And the answer is no. They have to be one of those 2. So these are disjoint events. And because these are disjoint events, I can follow through with my little formula. The probability of O positive plus the probability of O negative minus the probability of O positive and O negative. Well, the probability of O positive is 0.38. Probability of O negative is 0.07. Now let's talk about this one. Because they're disjoint, this probability goes to 0. And I could just have used that original formula for disjoint events. Now when I add these up, I get 0.45. And again, because they're disjoint, this intersection value is 0. Let's go ahead and look at another example. For this example, let's look at the probability that a person that's randomly selected is rhesus negative. That would mean O negative, B negative, A negative, or AB negative. So you should write all those out. So when we talk about these, I have all these ORs. Now remember, they can't intersect. These are disjoint events. So to find the probability of this event, I could just add up all the individual probability. 7% are O negative, 2% are B negative, etc. Now when I add these up, 7, 9, 15, 16, it looks like I get about a 16% chance that a randomly selected person is rhesus negative. So again, we can talk about all these different types of events. Let's go ahead and look at one more example. For this last one, I would like to know that a randomly selected person is either from blood group O or is rhesus negative. Okay, so Clearly, they can be O negative, so these are not disjoint events. So let's go ahead and look at our formula. This would be the probability that a person was O plus the probability that a person was rhesus negative, I'll go R negative, minus the probability that they're both O and rhesus negative. So filling out these probabilities, we've done this. We've done probability of O is right here. The probability of O was 0.45. The probability of rhesus negative we've done as well is right here already, 0.16. Now I need to look at the probability of both O and rhesus negative. Well, let's go ahead and look up at my table here. O and rhesus negative was 7%, or 0.07. So when I combine all these, I get 0.54. So about 54% of the population is either O or rhesus negative. So from data, we can actually find out a lot of different probability statements. And so it's kind of interesting to look at that. Now let's go ahead and look at another example. In this example, we're going to be looking at some characteristics. Excuse me. In this example, we're going to be looking at some characteristics of some dogs. Now this particular example about dogs also has to do with genetic traits. So we're going to be looking at two different characteristics of Dalmatians. We're going to be looking at H, whether they're hearing impaired, and we're also going to be looking at B, whether they're blue-eyed or not. Okay, so a couple of different things that we can look at here. First of all, could I have a Dalmatian that is both hearing impaired and blue-eyed? And the answer is yes. So these events are not disjoint. So that helps me right away when we're talking about our Venn diagram. Now usually in a Venn diagram, we just use circles to represent probability, and those circles are not proportional to the probability. So for instance, these are even circles, meaning they're the same size, but that doesn't guarantee that they're even probabilities. So just so you're aware. So here we have hearing impaired, blue eyes. Is it possible to be both? And the answer is yes. So let's go ahead and look at some different characteristics. From this particular Venn diagram, I want to fill out 5% of Dalmatians are both hearing impaired and blue-eyed. 23%, or 0.23, are hearing impaired but not blue-eyed. So from here we should be able to figure out all different sorts of stuff. So everything in green is information that was given. So let's go ahead and write that out. The probability of hearing impaired and, whoops, this is a symbol that means and. I'm just going to write it out though so I don't cause as much confusion. So hearing impaired and blue-eyed is about 5%. And then we also have the probability of hearing impaired and not blue-eyed. So that B prime is not blue-eyed is 0.23. Now, in order to figure out anything else, we need a little bit more information. And the other piece of information that we need is the probability. Well, we could have a lot of different things, but one of the pieces of information that would be helpful here is we could look at the probability of being blue-eyed and not hearing impaired. And that's going to be given as 0.06. So that would go up here in your Venn diagram. Okay, so this is blue-eyed and not hearing impaired in this right wedge. This middle wedge is hearing impaired and blue-eyed, and then this left wedge is hearing impaired and not blue-eyed. Now, first of all, let's go ahead and see some different probabilities that we could work with from here. So we could find, and again in red are the ones that I'm going to be finding, what's the probability of being hearing impaired and blue-eyed? Well, we can clearly see these are not disjoint events. That would be the probability of hearing impaired plus the probability of blue-eyed minus the probability of their intersection because we counted them twice. So for hearing impaired, that piece right here would be 0.23 plus 0.05. The probability of being blue-eyed is 0.05 plus 0.06 because I'm adding up these probabilities. And then you notice we counted this 0.05 twice, so now I need to subtract one of those out. So I'm subtracting that out because it was counted twice. So hearing impaired or blue-eyed looks like when I add all these up would equal 0.34 or 34% chance. So again, hearing impaired was the 23 plus 5 that made up this entire circle. So there's some interesting things that we can look at. Now if you notice, I basically add up these three pieces from the Venn diagram, so it's pretty easy to work with to get that 34% if I add up the 23, the 5, and the 6. Now also notice if I add those up, they don't add up to 1. Well, what ends up happening is out here there's other characteristics that are not accounted for. So out here I have 0.66, and that's the probability that I'm neither H, hearing impaired, nor blue-eyed for my next randomly selected dog. So again, a Venn diagram really helps us out here. A lot of people forget to fill in this piece right here, the neither piece. So keep that in mind when you're working with Venn diagrams because they really are helpful to organize information. So everything that we've been looking at so far has been discrete, whether discrete quantitative or discrete qualitative. The next thing I want to look at is continuous random variables. Now when we talk about continuous random variables, we are talking about quantitative, and again RVs stand for random variables, quantitative or numerical values. Now we're already pretty familiar with these actually because we've talked about stem plots, stem and leaf plots, box plots, etc. But when you have a continuous sample space, we have an infinite number of events. So a continuous sample space has an infinite number of events. And we don't want to write out an infinite number of events. In fact, I don't think we can write out an infinite number of events along with their corresponding probability. So because we can't write out all the different events and their corresponding probabilities like we did up above, we use density curves to represent probability. So we use density curves to represent probability. Now these density curves are basically like our stem and leaf plot, and we just smooth the curve. So for instance, we could have a symmetric density curve, we could have a right skewed density curve, we could have a left skewed density curve. So again, this is symmetric, this is right skewed or negative or positive skewed, and this one is a negative skew or a left skew. Okay, and we could have all sorts of different shapes. We could have some sort of a density curve that's uniform, meaning it has all the same values, so this is called a uniform density curve. And then I find corresponding probabilities that correspond with area. So for instance, if I want to find the probability that I have events between, let's say, A and B, I just find this area. Well, for a rectangle, that's pretty easy. It's just base times height. But as these curves get more complicated, finding the area underneath the curve to associate to probability isn't so simple. So in order to find probabilities underneath a curve, basically, when you want to find these probabilities are assigned for intervals. So I have to have a range of data that I'm looking at. So for this example, I'm trying to find the probability over the interval from A to B. But let's say I was trying to find the probability of C here, and that's just this point. There's no interval here. I can't do that for a continuous distribution, so I cannot find the probability of a single event. All my values have to be related to an interval. So again, events are defined over intervals of values, and the total area underneath a curve represents the whole population or sample space, so the total area underneath each one of these curves is 100%. And then because I have 100%, or if you want to think about it as decimals, 1, I can find corresponding probabilities. So this entire curve density is 1. or 100%. And then what I do is I find areas over in intervals for a particular event to try and summarize these. So let's go ahead and write all of that down. So again, events are defined over an interval of values, not just at a single point. The total area represents the sample space and should sum to 100%. And probabilities are computed as areas underneath these curves. Now again, up here it was really easy when we had the uniform distribution because I was looking at basically the area of a rectangle. Now over here in this particular case, this shaded area is a probability of a particular event A, and event A is given by this interval on the horizontal axis. And then what I try and do is to find this area, and that relates to probability. So area relates to probability. So the density curve represents both the population distribution and the probability model. And that is that the probability of an event corresponds to the frequency of that event in the population. Now note, the probability of a single value, like we did up here, is 0. I have to have an interval of values because I need two dimensions, base times height. Let's say to find the area of a rectangle. If I only know the base and not the height, I can't find the area. And if I can't find the area, I can't find the corresponding probability. So let's go ahead and look at an example of a very simple case with a uniform distribution, because we're really good with the uniform distribution because basically you're finding areas of rectangles. So let's go ahead and look at an example, and in this particular example we're using a uniform distribution. Now for this uniform distribution, I know its height, and because I know its height, I should be able to talk about its area and verify that the total area underneath the curve is 1. So when I find the area of a rectangle, it's base times height. This particular rectangle has a height of 1, and if its total area is 1, that tells me that my base also has to be 1. So the area here is base times height, which is 1 times 1, or 1. So there's my 100%. Now if I want to find corresponding distributions or corresponding probabilities, I just find the area. So let's go ahead and look at an example. Let's find the probability that, we'll call this x, my random variable x, is less than or equal to 0.5. Well, here's 0.5, halfway in between. So here's 0.5. Here's less than or equal to, so this is the area that I'm trying to find that will correspond to that probability. Well, again, it's base times height. Well, the base here is 0.5 minus 0, right minus left, and the height of this is 1 minus 0. So I have 0.5 times 1, so I have 0.5 as my probability. So 0.5 is my probability. Now remember, all probabilities should sum between, or should be between 0 and 1, and so this seems like a reasonable value. Now another way that I could have written x less than or equal to 0.5, this could have also been the probability that x was between 0 and 0.5. Now notice, whether I have an equal sign here doesn't matter. So that could have also been equal to 0, between 0 and 0.5 with no equal sign here, because there's no area above a single point on a curve. Let's go ahead and look at another example. Same distribution, so same picture. And for this picture, I would like to find the probability that we're between, let's say, 0.2 and 0.6. So here on my graph is 0.2, and here we are at 0.6. Now, two less than signs arranged in this manner mean between. So I'm greater than 0.2 but less than 0.6. So I'm trying to find this probability. Well, it's still base times height. Now when we talk about my base here, my base is 0.6 minus 0.2, and my height is 1 minus 0. So I have 0.4 times 1, which is 0.4. That's a probability that I'm in between 0.2 and 0.6 of this particular uniform distribution. Now note, this is so important. the probability that x is any particular value in this curve, and I'll say 0.5, could be any value, is 0. There's no area above a single point on a continuous distribution. Now for the same graph, let's go ahead and look at one more probability statement. So for this probability statement, I would like to talk about the probability that x is less than or equal to 0.4 or x is greater than 0.9. So how would this look? Well, here's 0.4 and here's 0.9, not really to scale. Greater than 0.9 is here. Less than or equal to 0.4 is here, so I basically find the area of each one. Well, the base of this one is 0.4, the height is 1. The base of this one is not 0.9, it's 1 minus 0.9, so for it has basically a base of 0.1, and its height is 1. So I get 0.4 plus 1 minus 0.9 is 0.1 times 1 is 0.1, so I get 0.5. So this area was 0.4, this area was 0.1, and I add them together. And then of course you can look at complements as well, and complements really make all this a lot easier. Okay, to finish up here, let's go ahead and talk about how we take probabilities and we transform them into comments about risks and odds of events. Okay. Now the examples that we're going to be looking at have to deal with the health sciences, but they're applicable in many ways. Like betting on football, you know the odds. You know, betting on a horse race, there's particular odds. But we're going to be talking about these in terms of health sciences. So again, if you talk about, you know, going in to see a doctor and you're diagnosed with cancer, you might say, well, what are my odds? And again, that's kind of a broad statement, but basically you're wondering, what are your odds of survival? What are your odds of not dying from this disease? But in the health sciences, they talk about odds over 5 years, let's say, or how long you might expect to live, or the percentage of people who might expect to live with this disease for 5 years, or 10 years, or 15 years. So to start out with, let's go ahead and talk about risk. The risk of an undesirable outcome is usually what we talk about here when we're talking about a phenomena, and we're talking about the risk of some event A is the probability of event A. So if we say that the risk of getting lung cancer if you're a smoker is, let's say, 64%, that's the same as the odds or the probability. And again, probability is based on long-term relative frequency. Now the odds is another story. The odds of an outcome of a random phenomena is the ratio. So there's a couple important words here. It's the ratio of the probability of that outcome over the probability of that outcome not occurring. So if we were to talk about the odds then, let's say the probability of event A over the complement 1 minus the probability of event A. So if the probability of event A was 0.4, the complement of that is 0.6, so this would be 4/6 or 2/3, which is about 67% odds. Okay, so again, when we talk about the risk and the odds, it's actually two different conversations. This is also the odds of 2 to 3 is another way we could talk about that, 2 to 3, if that were to reduce that fraction. So to finish up our basic conversation about probability, let's go ahead and look at one last example. So for this example, we're going to be looking at the risk of sickle cell anemia. I'll read through this. Sickle cell anemia is a serious inherited blood disease affecting the shape of red blood cells. Individuals carrying only one copy of the defective gene, the sickle cell trait, are generally healthy but may pass on that gene to their offspring. If a couple learns from prenatal tests that they both carry the sickle cell trait, genetic laws of inheritance tell us there is a 25% chance that they could conceive a child who will suffer from sickle cell anemia. What are the corresponding risks and odds? So let's go ahead and start with risks. So when we talk about the risk here, we're basically looking at the risk of sickle cell anemia. So the risk of sickle cell anemia is given up here. Is just the probability of sickle cell anemia. And that's given to us, 25%, 0.25. And that's if both parents carry the marker. Okay, now if we talk about the odds of sickle cell anemia, that would be 25% over its complement of 75. And if I reduce this fraction, this would be 1 to 3. So the odds in this particular case are 1 to 3, 1 to 3, or 33% chance that their child would have the sickle cell anemia. So again, you'll see it written as 1 over 3, 1 to 3, or 1 to 3. Now we are looking at extremely basic probability here. We're not looking at very complicated problems because we don't need to know all of that when we get to our next step. And our next step is using these to find probability statements. So everything that we've looked at today, some important things to remember, whether events are disjoint or not disjoint, the addition rule, and then talking about how we can calculate some basic number of outcomes. For instance, we have 3 children, 2 to the third is 8 different possible outcomes. So those are some basics that you'll want to be sure that you know how to work with. Stop.